Welcome all to Kinematics class 15, in which we'll discuss about the condition for collision. If we are considering a situation that there is an object of mass, let's say m1, is moving towards right with the velocity, take it as u1 through a surface, and take it as another object of mass m2 over here, which is moving with the velocity u2 towards right. And if these particles are keep on moving with the same velocity u1 and u2, so we know that definitely after some times they may make a collision. Same as like that, if you are considering a situation that there is an object 1 which is moving towards right with the velocity 20, and there is another object 2 which is moving towards right with the velocity 10. So we can say that in this situation also after some times this 1 will make a collision with 2. But if you are considering a situation something like this, there is an object which is moving along this direction with the velocity, take it as v1, and there is another object which is at this particular point, take it as object 2, which is moving along this direction with the velocity, let's say that is equal to v2. And our aim is to find out whether these particles will make a collision or not. So in this situation, it may be difficult to identify whether these two particles will make a collision or not. So there is a possibility of collision only if the particle 1 and particle 2 reach the point P, means the point over here, at the same time, then they can make a collision. Otherwise there will not be any collision. So over here the situation will be something like this. This one is moving with the velocity, let's say that is equal to v1, and this one is moving with the velocity, let's say that is equal to v2. So if both the particles are moving something like this, and if they be able to reach this point at the same time, then they may make a collision with each other. But there is another possibility, like if the velocity of v1 is more than that of v2, it may move something like this, so there will not be any collision between them. Or if this v2 is more than that of v1, or depends upon the distance and other things, so it may move something like this also. So there is a possibility of collision, or there is a possibility of there is no collision between this one. Then if both the particles are not moving in a straight line, it may be difficult to observe the condition for collision. So for observing this type of situation, we'll use a concept of relative velocity. Now according to the concept of relative velocity, we can observe the velocity of one object with respect to another. So if we would like to keep the particle 1 at rest and we want to observe the velocity of 2 with respect to 1, then what we'll do is we can reduce the velocity of the entire system by v1. That means we are reducing the velocity of first particle by v1, and we need to reduce the velocity of second particle by v1. So that is known as the velocity of 2 with respect to 1, velocity of 2 minus velocity of 1. So over here you can observe that this first particle become rest, and we can find out what about the relative velocity of second particle with respect to first particle. So let's say this one is representing the velocity v2, and let's say this is representing velocity v1, and assume that if you are going for vector addition, and after vector addition if you are getting the resultant velocity vector along this direction, so let's say this is velocity of 2 with respect to 1, it can be in any direction. I'm just considering a situation that if velocity of 2 with respect to 1 is along the line joining 1 and 2, now we can just consider the situation something like this. There is a particle 1 which is at rest, and there is another particle 2 which is moving with a relative velocity along the line joining 1 and 2 with the velocity v21. So in this situation there is no doubt that if 2 is moving towards 1 or along the line joining 1 and 2, then definitely after some times this 2 is going to make a collision with 1. So this is a condition for collision. We need to find out what about the relative velocity of 1 with respect to 2, 2 with respect to 1. And if relative velocity of 1 with respect to 2, 2 with respect to 1 is along the line joining them, definitely they will make a collision. If it is not along the line joining them, then there will not be any collision. That means, assume that if you just calculate the value of velocity of 2 with respect to 1, and let's say this is representing the velocity of v2, and this is representing the velocity of v1. And if you are going for vector addition, and after vector addition assume that we are getting this is the direction of velocity of 2 with respect to 1, and it is making some angle, let's say something like alpha over here. So with respect to 1, if this 2 is moving in this direction with the velocity v21, so definitely we know that this 2 is not going to make a collision with 1 over here. So the condition for collision is velocity of 2 with respect to 1 should be along the line joining 1 and 2, then it can make a collision. So to occur collision between particle 1 and particle 2, the relative velocity of 1 with respect to 2 or the relative velocity of 2 with respect to 1 should be along the line joining 1 and 2. Now in questions they may ask to find out whether they will make a collision, and if there is a collision then what about the value of time taken for its collision. So let's discuss that part. So if you are considering that there is a particle 1 which is moving along this direction with the velocity, let's say v1, and this dotted line represents the line joining particle 1 and 2, and this point particle 2 is moving along this direction with a velocity, let's say, that is equal to v2, and let's say this is making an angle theta 1 and this is making an angle theta 2. So first situation was we need to check it whether they are going to make a collision or not. So as we discussed, we can reduce the velocity of first particle by v1 or the entire system by v1. So velocity of this 2 is also decreased by the same value v1. So as this angle is theta 1, we can write this angle should also be equal to theta 1 and this angle should also be equal to theta 1. So now we are keeping this for particle 1 at rest, and if the velocity of second particle is along the line joining 1 and 2, so this is the velocity of 2 with respect to 1, then they will make a collision. And let's say the initial distance between the first particle and second particle is L. So we are going to find out what about the value of time taken for its collision. So you can write the value of time will be equal to time taken for collision will be equal to distance traveled divided by the relative velocity, that we can take it as v21. Now discuss how to find out the value of this v21. So for the calculation of v2, velocity of 2 with respect to 1, v21, so we discussed that velocity of 2 is along this direction, let's say that is v2, and this angle, let's say that is theta 2, and velocity along this direction, take it as v1, and this angle is equal to theta 1. So we can resolve these velocities into its component. Velocity of v2 along this direction can be written as nothing but v2 cos theta 2, and velocity along this direction we can take it as nothing but v2 sin theta 2. Same as like that, if you are resolving velocity v1 into its component of v1 along this direction, we can take it as nothing but v1 cos theta 1, and velocity along this direction we can take it as nothing but v1 sin theta 1. So if the resultant velocity is along the line joining first and second particle, then this vertical component of velocities, that is v2 sin theta 2 and v1 sin theta 1, should get cancelled. So one condition we can write the value of v2 sin theta 2 should be equal to nothing but v1 sin theta 1, and the sum of this v2 cos theta 2 plus v1 cos theta 1 is going to give the value of velocity of 2 with respect to 1 along the line joining 1 and 2. So we can write v21 is equal to v2 cos theta 2 plus v1 cos theta 1. So you can write the value of time taken for collision is equal to distance L divided by their relative velocity, that is v2 cos theta 2 plus v1 cos theta 1. So this is the value of time taken for collision, and this is the condition for collision. Now if the relative velocity is not along the line joining the point 1 and point 2, so as we discussed, we know that they are not going to make collision. So in this situation, they will ask to find out what about the value of minimum possible distance between these two particles particle 1 and particle 2. In this situation also, it is difficult to observe the condition if both the particles are moving. So for the calculation purpose, what we will do is we'll keep one object at rest. Means we are going to reduce the velocity of entire system by a factor. Let's say that is v1, and here also we are going to reduce its velocity by v1. So we can say that the first particle will come to rest. So we are keeping the first particle at rest. That means we are going to observe the velocity of 2 with respect to 1. So over here, if you are taking, this is nothing but the v2 vector, and this is nothing but minus v1 vector. Let's say after vector addition, we are getting the resultant vector. Assume that the resultant vector is along this direction. Let's say this is v2 1, velocity of 2 with respect to 1, and assume that it is making some angle theta over here. So we can just consider that now the situation becomes, there is an object 1 which is at rest, and there is another object 2 which is moving with the velocity along this direction, or which is moving with the relative velocity, which is v21, and it is making an angle theta over here. So if the particle is moving through a path something like this, now we know that collision is not going to happen. So in this question, they will ask to find out what about the minimum possible distance between particle 1 and particle 2. So if you are assuming that particle 1 is at rest, then particle 2 is moving through a path something like this. So we can observe that this is going to be the minimum distance if we are dropping a perpendicular over here. So we can say that this red line represents the minimum possible distance between particle 1 and particle 2. So we'll discuss how to find out the value of this R minimum. Now let's say the distance between particle 1 and particle 2 is represented by nothing but L, and if you know that this angle is nothing but theta, so we can write from the definition of sine theta, which is opposite side, that is R minimum, divided by the hypotenuse, which is L. So we'll get the value of R minimum is equal to nothing but L sine theta. Now in question they will give the value of L. Now we'll discuss how to find out the value of sine theta over here. Now for the calculation of sine theta, we can just consider that there is particle 1 and this particle 2, and we discussed how to find out the relative velocity. So initially we are having a velocity vector, that is v2 vector, and another velocity vector along this direction, that we can take it as nothing but v1 vector, and this angle is nothing but theta 1, and this angle is nothing but theta 2. Now if you are finding out the components of these velocities along the line joining 1 and 2 and perpendicular to that, so you can write the component of v2 along this direction is going to be v2 sine theta 2, and the component of velocity along this direction is going to be v2 cos theta 2. Same as like if you are resolving this v1 into its components, so components of v1 along this direction is nothing but v1 sine theta 1, and the component of velocity along this direction we can take it as nothing but v1 cos theta 1. So if you are considering the resultant velocity, means the velocity of 2 with respect to 1, we got the resultant velocity, let's say along this direction, and that is taken as nothing but v21, and we assume that it is making an angle theta with respect to the line joining particle 1 and particle 2. If you are resolving this into its components, so component of v2 along this direction, we can take it as v21 cos theta, and component of v21 along this direction, which we can take it as v21 sine theta. Now we can say that the component of resultant velocity in upward direction, which is v21 sine theta, is equal to nothing but the sum of velocities of v1 and v2 in upward direction, because while adding v1 and v2 vectors, we are going to get the v21 vector. So you can write this as equal to v2 sine theta 2 minus, I'm just writing negative sign because v1 sine theta 1 is in downward direction. From this we can find out the value of sine theta over here. Now in some question they will ask to find out what about the value of time taken to attain this minimum distance. So we can say that this particle 2 with respect to 1 is moving through this much distance before it is reaching this minimum between point 1 and 2. Let's say this point is represented by point C. Now from this triangle we can write this distance is going to be nothing but L cos theta. So we can find out what about the value of this time taken to attain this minimum distance. That will be equal to distance, which is L cos theta divided by velocity, which is equal to v21. So over here, for the calculation purpose, we should know what about the value of cos theta over here. Let's see how to find out the value of this cos theta. So from the previous diagram, we can find out the value of cos theta also. The component of resultant velocity along x-axis or along the horizontal directions was v21 cos theta. That we can write is equal to the sum of component of v1 vector and v2 vector. So that is going to be v1 cos theta 1 plus v2 cos theta 2. So from this equation we can find out the value of cos theta. Hope so that you understood whatever the things we discussed in this class. If you are having any doubt, please contact. Thank you.